All right there. Hi everyone. Yeah, so we're back with another little live stream here. I'll get my code share going. Oh, sure I don't have an echo of myself going. Anyway. Cool. So yeah, let's share screen. There we go. Just need to close that. Yeah, so we'll be working more on this plugin today that I've been talking about the last little bit. Cool, yeah, so this is the multi-tool plugin that we'll be working on again today. And yeah, let me reset my font sizes so it's a little easier to see. I'll go a bit bigger than usual today. Cool. Yeah, hopefully that's big enough for everyone. Everyone can see that pretty clearly. Cool. So just a little recap of what we've got in the plugin today. So yeah, so this is the plugin just like basically as it is, and then we can choose a tool. So you've got our EQ, which doesn't really have a UI, Waveshaper, which we'll be working more on today. We've got this signal generator that just right now is just generating a sine wave. Oops, yeah, I don't know, the controls are a bit wonky, but you know, it's kind of where that's at. We've got this Pultec style EQ, which we've talked about before, and I'm sure we'll come back to. We've got this little band splitter, so this is just like a high pass, low pass crossover filter that splits the signal into two output channels. We've got this brick wall, which I thought I had spent some time doing the UI for this, but maybe I haven't done it yet. And then we've got this state variable filter, which I think we've also talked about on stream before. So yeah, today we'll be talking a little more about the Waveshaper. Let me just make sure that all my settings are good here. All right, cool. Yeah, so yeah, I wanted to talk a little bit today about Waveshaping and specifically about aliasing suppression, because that can be kind of a tricky thing with Waveshapers. So first off, let's get some basic input into the Waveshaper and a little visualizer so we can see what's coming out. I'm going to mute the output just because I don't really want to have to listen to a sine wave for the next while. So we've got a tone going in, and then we'll put an oscilloscope here on the output so we can see what's coming out. I'll make it a little bit bigger. Actually, I'm going to make it even bigger than that. Cool. So this should give us a pretty good view into what's going on. And then, yeah, we'll just put up the gain and maybe turn down the frequency a little bit so it's easier to see. So yeah, here we've just got a plain sine wave. And then you can see that maybe we can clip the sine wave a little bit. Maybe do that. Yeah, so it's getting a little bit of odd stuff out of the Waveshaper today, but yeah, that should give us a decent idea of where we want to go. We've got ninth order polynomial clipping. We've got full wave rectifier. That's pretty fun. We've got these kind of wave folder type things that are also a lot of fun. This is like a West Coast style wave folder. Yeah, so I probably want to spend some time with this just to kind of normalize some of the different output levels, since like specifically this one tends to be kind of loud and the wave multiply tends to be kind of quiet. Oh, sorry, am I confusing them? Oh, okay, yeah, wave multiply Tends to be kind of quiet. There it is. Okay. Yeah, for some reason the oscilloscope here doesn't want to reset itself as much when we're using this one. That's okay. Anyway, so we'll talk about that stuff a little bit, but more what I wanted to talk about was this funky little wave shaper that I found yesterday on the Audio Programmer Discord. So this is something that the Signal Smith fellow, I'm forgetting his name at the moment, but yeah, he does some great work with reverbs and limiters and plenty of other things. But this was something that he had posted on the Discord, and this is kind of a cool little wave shaping idea here. You've got some funky shapes that you can make with it. So it's sort of like well, kind of the way that I see it is that you've got sort of this sine wave where the frequency of the sine depends on your amplitude, where your amplitude is sort of the amplitude of this input x. And so yeah, you've got a few kind of funky, I don't know what to call it, but some funky shapes. So I feel like this is, at least in my opinion, kind of the basic shape where it's like a sine wave going flat across, and then as you move this k parameter, it kind of becomes more like a line. So yeah, it becomes more linear as opposed to more, I guess, flat, you could say. And then this sort of controls, this m parameter here sort of controls the frequency that you're looking at with the sine wave. So I thought this would be kind of a cool wave shaper to look at and think about antiderivative, anti-aliasing and stuff like that. Yeah, so this is kind of the basic function. And so we're gonna look at this and see if we can implement a version of this that sounds good, doesn't have too much aliasing, and hopefully isn't too heavy on the CPU. So yeah, let's take a look at that. So if we're going to do antiderivative anti-aliasing, we're going to need some antiderivative here. So for now, we'll just say it's the same. We'll just say it's f1, which is the first antiderivative, equals x. Obviously, that's not correct, but that'll get us something to start with. And then we'll do the same thing for the second antiderivative. We can go up even further to higher antiderivatives if we want, but I usually don't, just for reasons. So yeah, I guess the first thing I'm going to do is sort of rethink the way that this initial nonlinearity is, or this initial wave shaping function is formulated. So right now we've got x times this whole thing. And I would rather not have this large sort of product here that'll make the antiderivative stuff a little tricky. So I'm going to put the x here and sort of multiply through the x, which gets us the same function, just in a slightly different form. So next we're going to need the antiderivative of this first term here. And so this actually isn't too bad. Maybe I'll move this in a level here. I don't know. Doesn't really make a difference, but that's okay. So the antiderivative of x is going to be x squared over 2. So we can just do that here. Okay, yeah, so we should get that. Interesting that this is fairly small, I guess. Oh, that's because we have k like that. Okay, yeah, so depending on what we do with k, that will change the shape of our antiderivatives, which makes sense. And then let's do the second antiderivative as well. So this is going to be kind of a similar thing where we're just going to do to the third power and then times 3 here. So that'll be 6. And again, we get some kind of cubic function here, as opposed to the quadratic function that we get for the first antiderivative. So now we've got this more complicated thing that we need to do for our second term. So the k is just going to be a constant, so we can kind of pull that out. And then I'm going to pull up, I already got Wolfram alpha here, so I'm going to use that for the second term. So we've got k times the sine of m times the natural log of absolute value x. Okay, so integral of x times the sine of m times the natural log of absolute value x, and then want all that with respect to x. Okay, so it doesn't like this input. Indefinite integral assuming all variables are real. Well, that is true. All the variables are real. Let me ignore the absolute value of x just for a moment and try this. So that's a pretty manageable result. And then what if I do natural log of minus x on the other side? Okay, so that ends up being more or less the same actually, right? So if x is greater than 0, then we get the previous version, and if x is less than 0, then we get this version. So I think that should work out, just keeping it as absolute value x in there, but maybe not. We'll find out. Sorry if I'm being a little vague here. All right, yeah, so let's try doing this term just kind of as it's written here. So we've got x squared. So let's see, we've got a fraction here. X squared times x squared times, maybe click there, 2 sine m log x. And so here, when they say log, they really mean the natural log. And then I'm going to keep the absolute values here for now. We may need to get rid of that later, but we'll find out. And then we've got another term here. So this is m cosine m log x. And again, I'll throw the absolute values in there for now. And that should be our numerator. And then on the bottom, we've got m squared plus 4. Okay, yeah, so that looks pretty reasonable, actually. Yeah, kind of getting what I would expect out of that. That's kind of interesting. Yeah, that's a pretty neat function. I'd be curious. Maybe I should ask Signalsmith how he thought of this, or what his inspiration was for this. I know he's pretty high level math fellow, so yeah, I'm sure he's got some ideas about how these kinds of things can work. Anyway, so now we've got to figure out the second antiderivative. And so for this, we can kind of build on what we've got here, because this first term in the fraction is actually just the original term that we had. So now we've got x squared outside instead of just x. So I'm actually going to split this up and maybe try to think about it in a way that will make the second antiderivative a little easier to work with. So let's see here. We've got k x squared. We'll say 2kx squared right, times, actually, let's do all of that over m squared plus 4. Actually, I'm going to get rid of the x squared, pull that out here. So we've got x squared times this same term here, the sine m natural log x. Right? And then we've got a similar kind of thing here, where we've got a minus, this will be a minus, this time it will just be mk over m squared plus 4. And then we've got a similar term as we had here, but with a cosine. So I'm imagining there will be some ways to simplify whatever Wolfram Alpha gives us for this, just because of all the sine and cosine identities that may come about. But let's see what we get. So x squared here, and then cosine of that. Oh, and then this should be lowercase k. Cool, yeah, so that looks about the same. But it should be a little easier to work with now because we've got these separate terms that we can think about. So let's look at this term first. So we've got this constant out front. And then we can plug this into Wolfram Alpha and get our integral. So instead of x, we'll have x squared. And hopefully that doesn't make it too much more complicated. Okay, that actually looks fairly similar to what we had last time. That's kind of neat. All right, so I wonder if there's a way to copy this that Desmos will accept. I'm guessing there won't be, yeah. So let's see here, we've got, x cubed in the numerator, we've got, what was it, m squared or m cubed? M squared plus 9 in the denominator. And then we've got something here kind of similar to what we had before. So it's 3 sine m log x instead of 2, which is what we had last time. So this is 3 times the sine of m natural log of x. So yeah, that's more or less what we had before. I'll close that up, and then minus m cosine. So cool. So that's the first term of our antiderivative here. And now we should need just one more term. Well, it's kind of interesting. I'm actually not seeing much difference between what we had with this term and what we had without this term as far as the green line that's showing our second antiderivative, but maybe that's something we'll see in this next step. So again, I'll continue moving the constant along here. And now we should have a similar integral, but with cosine. Yeah, that looks right. Oh, hey guys. Hey, George. Yeah, this looks similar. Yeah, this looks about like what we would expect. So previously we had 3 sine m log x, and now we have m, and so the 3 and the m have kind of switched places from what we had in our previous one, which makes sense just because of the trigonometric identities, I guess. Yeah, so there's got to be a way to sort of combine these, but I'm just gonna I'm just gonna write it down first, and then figure out how to simplify it after. So let's see, we've got M and 3. Cool. Yeah, that's interesting. I'm not seeing a ton of difference between some of the different settings with this second antiderivative here. I wonder if I did something wrong. Let me get rid of this term just to see what we get. Well, maybe it's because we're looking at this range from like -1 to 1, and typically in that range, the x cubed value is going to be pretty small. Okay, so yeah, we are seeing some ripples there. It's not a huge, it's not going to be anything huge, but we are going to see something. That's interesting. Neat. Oh, what did I do? I lost, there we go. Okay, I lost the red curve. That's the first one, so we definitely don't want to lose that. Okay, yeah, that looks about right. And now let's bring this term back in, since we are going to want it. Okay, yeah, so if we go to larger values outside of 1, +1 and -1, then we start to see some of the differences there. That's kind of cool. All right, so now let's think about how we can simplify these guys here. So I'm going to start by just copying it into a new field here, and maybe we'll call this F2 2P just to differentiate it, and I'll give it a different color too, just to make it a little different. So first I'm just gonna split up some terms again. So let's see here. If I get rid of this and then put it here in like another subtraction term. So we've got this, we've already got the subtraction, so I don't need that again. We've got the same denominator that we had before. And then we also need to bring along the x cubed. It's important. Okay, so I messed something up. What did I mess up? X cubed 3 sine of x. Oh, I didn't bring along this constant term as well. Yeah, there we go. That looks about right. Actually, you know what? I'm gonna make this line dashed as well, just to make it a little bit easier to see that these two lines are overlapping. Cool, so we've got this term, and then we're gonna do basically the same thing with this fraction here. So I'm gonna take that term and bring it over here, again with the same denominator. And we're gonna need the same cross terms as well. So we've got that. And we've got an x cubed here. Yeah, I'm going to bring out the x cubes. The x cubed is always the first term in the fraction. Actually, you know what? Well, there are some things that we can do to simplify this. I don't know if I should start doing that immediately. Yeah, I'll do that first. So let's see. We're going to do x cubed over m squared plus 9 out here. And then we can just get rid of all of these fractions because the m squared plus 9 is going to be shared by all of them. And we can get rid of the x cubed. So we'll do a big set of parentheses here, and we can get rid of x cubed. There we go. Okay, I think I messed something up because it looks to me like our lines are getting off. Yeah, okay, so what did I do wrong? What did I do wrong? X cubed, m squared plus 9. Oh, you know what it is? These other constant terms were not divided by m squared plus 9. So I kind of need to account for that. This is a little ugly, but maybe it's not going to be that bad, I think, as we go a little further here. At least that's kind of what I'm hoping. Okay, apparently that did not solve it. All right, so let's go back a bit and see where things got off. So we've got this whole fraction up here. And so we should be able to pull out an x cubed, and we should be able to pull out 1 over m squared plus 9, right? Oh, you know what it is? I didn't propagate this minus sign here correctly. So see how the sign term should get the minus from there, but then this was a minus, and this should actually be a plus because we had a minus times a minus from there. And that's it. Now we're looking good on the graph there. So what can we do next? So let's swap around the location of some of these terms just to make it a little bit easier to see here. So I just switched the sine and the cosine there. So now we've got all the cosines on the right and all the sines on the left. And now we should be able to factor out this sine term and just make it, yeah, just make it that basically. Right, yeah, that looks correct to me. And then we should be able to do the same thing here, right? The difference is that the other term is the one being subtracted. So we can probably do the same thing where we just propagate the minus sign through. And that looks about right. Cool, yeah, that looks pretty good actually. And so now we can just make this term a bit simpler. So we can move the 6 up there. So now it's 3. Oh, sorry, move the 3 up there. So now that's a 6. We can make this m squared and get rid of the m here. And then this is a common denominator. So let's do 6k. Oh, and we can pull out a k too, you know. So let's bring a k term out here. And then we don't need the k's in here anymore. Sorry, I know it's always hard to follow along with someone else's algebra. That's just kind of a classic difficulty, but hopefully this isn't too hard to follow along with. So if I move the m squared over there, then I don't need that term anymore. And so now I've got this guy, and I'm going to get rid of the parentheses here just to clear that up a little bit. And what's neat is that that's actually the same term that we had over here. So now I don't need that at all. Right? No, apparently not right. All right, what did I do wrong? Oh, I see. Okay, yeah. So this is 2m and 3m. Really? That seems kind of strange. Interesting. So the cosine terms that we had were m and 3m. I don't think that's right. I think I made a mistake somewhere here, but where would it have been? Actually, let's not go back. Let's stay here for now. Okay, so that's looking right. But is it right? Yeah, these algebra problems are always a difficult time here. Yeah, let's see. So here we had 3 sine of m, and here we had m sine of m, but here we had 2 times 3, and here we had m times m. Whereas here we had 2 times m, and here we had m times 3. Okay, yeah, that works out right. Okay, yep, that makes sense. So here we have 2m minus 3m, so this can just become minus m. And then we don't need that anymore. And then this can just become a plus, and we don't need the minus. And now let's get rid of the parentheses for this guy as well. Oh. And there we go. So we've got our first and second antiderivative of this original function that we were dealing with here, which is this red wave shaping function. So yeah, I'm gonna not plot that one anymore since we've got a simplification that I'm pretty happy with for this. Okay, cool. So now I guess it's time to do some implementation. All right, yeah, let's see if we can get this working in the plugin. I'm excited to see how this works. Yeah, so this is always also the kind of thing where there's like a ton of little math optimizations that can be done. But yeah, we'll just get there as we go. Yeah, I'm sure there's going to be some things that can be optimized here and there, but actually, should we do that now? I'm gonna say no. Yeah, we'll get to that when we're ready. Oh, George wants to look at some nonlinear WDFs. I don't think I'm going to go into WDF world today. I think I'm going to stick with just these wave shapers. But maybe if we have time, we'll see how long some of this stuff takes. Cool, yeah. Does anyone have questions about this this wave shaping function? I can try to answer them as best I can if folks have things they're curious about. All right, so let's see what we've got in the plugin here. What does it sound like? Well, I don't have it implemented yet, so it's a little hard to do a sound demo, but I can do that in a moment here once we've got it implemented. Although I don't know if I have everything set up to get my audio going out to the stream, so it might be a little tricky. But good news is that the plugin here is open source and it'll be available soon. I'll have a build pipeline set up fairly soon, so hopefully you can try it out when that's ready. And yeah, once I have the implementation working, I'll see if I can get the audio routed into Zoom, even if it's just a temporary thing. Oh, was there a specific goal in mind? Not really. I just thought it looked cool. Yeah, I don't know. I kind of go back and forth between things that are like sort of designed intentionally and things that are just like, oh, I bet that would sound interesting, or I bet that would sound cool. And this was more of just a thing that seemed cool, so I figured I'd try it out. But yeah, so we'll see what we get here. So yeah, I guess we need a name for this if I'm going to make a file here. Also, I should save this and give it a title here. So let's see, maybe we'll call this Yeah, I don't know what's the right name. Does anyone have an idea for the name? I don't know. I could call it Signal Smith Shaper since he's the one I got it from. Yeah, we'll just call it that for now. Yeah, we can decide a different name later if we prefer. So we've got we've got our file here. I'll put this in namespace. I think this is the right namespace name. Yeah. Okay, Leon wants to know, is it possible to emulate a solid state system with just wave shaping? I guess it depends on what you mean by a solid state system. Like, yeah, I'm gonna, it's a little hard to guess what you mean, but since you use the word state there, I'm gonna say no. Just because usually a state, like a system that has state, a wave shaper is not good enough, or does not have enough information basically to emulate that kind of system. So yeah, generally if you have a system with state, then you need to model it with a stateful system, and a wave shaper, or at least the kind of wave shaper that we're working with here, is a memoryless system. But yeah, I mean, I might not be understanding the question perfectly, so yeah, definitely let me know if there's more specifics there. So so let's see here. Let's set up our class here. So we're gonna want some kind of I guess we're gonna want some kind of prepare function, but we're probably not gonna want that much stuff in it. And we're gonna want some kind of reset function. And then we're gonna want to process a block. And I'll think more about this once we're ready. All right, cool. So I wanted to have a look at my existing implementation of antiderivative, anti-aliasing Waveshaper. Okay, Leon's asking about a circuit with capacitor, resistors, and transistors. Yeah, so the tricky thing is that capacitors are a stateful circuit element. And so, yeah, if you have a circuit with a capacitor in it, then a Waveshaper is not going to be a very good way of emulating it. Unless, I mean, it depends on how the capacitors are used. Sometimes the capacitor can be kind of ignored because it doesn't actually affect the sound, at least in the audible frequency range. But in general, the answer would be no. Like if you have a circuit with a capacitor, then you would need a different way of emulating it that does not use Waveshapers, or uses Waveshapers along with other things. Yeah, so here's where we've got some actual ADAA equations worked out, but let's see. The way that I have things implemented here is kind of dependent on lookup tables, which is not what we're doing here. We're going to do things directly calculated rather than using a lookup table. So we're going to have to think about things a little bit differently. So let's see, we are still going to need the same state that we had previously. So I'll pull that over here. And also I'm going to include this just because I want to get some code completion and stuff, which I think I'm not getting now, partly because the file is not included anywhere. But anyway, so if I'm gonna do a prepare method, all I need is the number of channels, and then I can do something similar with the reset function here. So okay, cool. And then we've got some processing stuff. Yeah, let's see how we want to do this. So I'm going to say that we want a buffer view of floats. I mean, we could do doubles. We're going to want doubles eventually, but I'm going to say floats for now. And then we'll convert back and forth to double inside this. So yeah, this is kind of the inner loop here that we're going to want to do. So let's set this up kind of in a similar way. So first I'm going to loop through my buffer. So we've got our channel and we've got our data. Buffer iters, and we're going to iterate through the channels of the buffer. And so this we can set up in kind of a similar way. This is something I actually spoke about last time when I was talking about memory things. Yeah, I can explain it again if people are curious, but basically we're going to want these values here to store our state kind of temporarily while we go through this tight inner loop. Okay, I guess this needs to be a size t. That's a little annoying. Okay, I've got a question. Is your anti-aliasing a property of the function, or is that implemented separately, i.e. oversampling / filtering, etc.? So the way that the anti-aliasing is going to work is basically, so we've got this original function here, which is f of x, and then we've also got the first and second antiderivative, which are these two other functions here. And so basically, the way that the anti-aliasing works is that we're sort of doing a time domain derivative of these antiderivative functions, and that's what's going to actually give us our waveshaping function. And so because we're doing that in discrete time, that helps with the anti-aliasing of the waveshaper. And then I usually combine that with a little bit of oversampling as well, which is implemented kind of one level higher up than what I'm writing here. So the waveshaper processor is going to do the oversampling, and then that's going to give a buffer to this process block method here. So if there's oversampling, it will have already happened by the time we get here. And so once we're in here, we just have to implement the antiderivative stuff to get some extra anti-aliasing and so on. So now I'm going to iterate through the channel and basically do all of the stuff that I've laid out here. So let's see what we can do. So we need a tolerance, and then we need a few other things here. So we've got X, that's good. We're going to need our calc D1 and our fallback method. And then we're going to need our tolerance. Where do I define the tolerance here? It's been a minute since I looked at some of this code. Tolerance. Okay, so let's see how you want to do this. So this is going to be a scientific ratio kind of thing, which I've defined here. So this is going to be 1 times 10 to the minus 2. So we could do something along those lines. Then I'm going to want the double value of that. Maybe we'll go down a little bit. We'll see how that, we'll see how that goes. See if we like it or not. Okay, so now we need this fallback and calc D1 stuff. These functions tend to have a lot of arguments, and I feel like I'm going to need even more shortly. So I'm a little bit concerned about that, but maybe that's okay. Well, maybe we can use a lambda to get around it. Well, that can be difficult too for other reasons. So here in calc D1, we've got x0, we've got x1, 82x0, and 82x1. Okay, maybe that'll be fine. Yeah, let's try bringing this guy along as a lambda. Got a capture list there. Okay, and then we're going to need some captures. So we're going to need x1. We're going to need 82x0. We're going to need this. Oh, where'd we go? As a capture by reference. And then we're going to need a, what else are we going to need? Actually, it's gonna get a little tricky. Okay, yeah, let's do it this way. So I'm gonna say, yeah, we'll do it this way. So we'll say x1 equals x1 dot get. Oh, that's gonna be a problem, isn't it? Yeah, okay. This is a little bit annoying here. Anyway, let's finish up what we've got here. So and 82 x1. So now here we're going to have to do our dot gets. So yeah, this will be a little bit annoying just to have to type this so many times, but it's not the end of the world. Cool. And then when we actually call this down here, we're only going to need to call with a single argument, which is kind of nice. And so yeah, then we're going to need these NL func things. So I'm just going to copy those over from here, except that I'm going to take out their definitions because we don't have lookup tables in this implementation. Oh. So for now, I'm just going to do return X. And we're going to make these static this time as well. Oh, I guess that means they can't be const. That's fine. Yeah, so we'll see how that can be done in a minute here. What did we do wrong? Okay, this needs to be a .get as well. And then we're going to want our fallback next. So we can do kind of a similar thing where we have our lambda here, const auto. Cool. So now we've got a fairly similar thing, except that we're going to want some different captures. So let's double check how we were calling this before, just to make sure that we get the correct captures. So x1, x2, and 82, x1. Cool. Okay, so and then we're going to want to do the same thing that we did before, where we have all of these call.get, which, yeah, again, a little annoying, but not the end of the world. Just a little extra typing. Okay, cool. Yeah, so that should be everything we need to get the ADAA implementation working. And then I'll cast some stuff back and forth to a float here, maybe. Well, let's do some things a little different. So we've got x float, and then we'll have be a double cast. I don't know. This might not be the cleanest or most efficient way to do this, but for now it's okay. We can optimize it a little bit later on. And then we're updating our state after, so that should be all right. Cool. So now we just need to go in and actually implement these nonlinear functions. So let's do this. Let's do this now. So we're going to need, now we're going to need our sort of parameter values, which are this K and M, these K and M things. So we should think about that a little bit. We're also going to need these kind of more expensive things to calculate, which are the sine of M and, yeah, sine of M and cosine of M, natural log, absolute value X, because those are needed. Like we need the sine version 3 times and the cosine version twice. So let's not recompute those if we don't have to. And yeah, there's probably some other things that we can clean up a little bit. But yeah, we'll get to that. We'll get to that when we get to that. So yeah, first let's look at our parameters. So this will be our K. We'll call it K smooth, and then we'll have M smooth. I don't really like how that looks. Maybe I'll use sort of this way of writing it instead. Doesn't really make too much difference. And then, so this is just a 0 to 1 parameter, so a linear scale is probably fine. This is going from 5 to 50. So yeah, maybe we'll need like a multiplicative scale. I'll think about that a little bit. Okay, so for this, I am going to need a little bit more info. So I'm going to need the sample rate and the block size. So let's see, we've got k smooth dot prepare sample rate and block size, and we'll do the same thing with m. And then how do we want to do this from there? So k smooth, we'll have the ramp length like that, and we can do the same thing with m smooth. Yeah, like I mentioned, I'm going to start m smooth as a value smoothing type multiplicative, just because it never goes below, in our case, 5. But yeah, we'll see. We'll see what we end up doing with that. Yeah, it'll probably be fine. Cool. So now when we take in our processing function, I'm also going to take in a couple of parameters. So we'll have our k param and our m param. And then I'll do k smooth dot process. This will be k param, and we'll do maybe num samples for this. Get num samples, so we'll use that here. And so what this is going to do is it's going to run basically it's like a juice smoothed value, and it's going to run this for us once, and then we can reuse it across all of the channels that we're processing. So yeah, something that kind of bugged me about the juice smoothed value is that you either need to have one smoother for all of your, for every channel in your buffer, or you need to process your buffer by channel first and then by sample second. And I prefer to do, well, I guess it's flipped, but like your innermost loop, I like to have my innermost loop be sample wise and the outer one be channel wise. But if you only want to have one juice smooth value, then you kind of need to flip it. And I didn't like that very much. So that's why I set up these other things here. So next we'll do we'll have our k smooth data be get smooth buffer for each of these. So we'll have k smooth data and m smooth data, so we can use that later on. So now what we're going to need is we're going to need x, we're going to need k, and we're going to need m down here in this function. Ooh, maybe we should make these doubles instead of floats. That might work better for this particular case, which probably means we're going to need to change these to doubles as well. Yeah, that'll make things easier in a second here. So yeah, now when we call nlfunc, well, first I'm going to reorganize this a little bit, but we're going to need to call it with k smooth data, n. Okay, I guess we need a little more information passed around here. So we need to know the sample index, so we can do that. And we need to have k smooth data captured here. And then we're also going to need to have M smooth data captured here. So we can do the same thing here. So this is M smooth data. So we've got K and M going into that function. And now we also need to have the sample index going in here. So in order to do that, I'm going to change the way I'm iterating over this. So I'm going to have N and X float coming out of data, but we're going to enumerate over it. So this is like kind of similar syntax as what you would have in Python, just for iterating over something that you can iterate over. And then we'll have N that we can use there, which is kind of handy. So yeah, now we've got our K and M parameters getting into that function. And I guess we're going to want the same thing with our other two functions as well. So maybe I'll pass those down. Okay, so now we're probably going to need a little bit more sort of wrangling to get these other things working the same way. So let's see. I've got that. I've got the sample index here. And so I can use those when I call these functions here. Oh, I messed that up. I messed that last one up. We want this inside the parenthesis there. All right, there we go. Interesting. Okay, so we may not be able to share everything with our other calculations between some of these, but that's okay. NLFunc is that set of parentheses, so let's do that. Okay, so that I think will work. Tricky thing now will be getting a reasonably optimized version of these antiderivative functions into these functions down here. So yeah, this will be interesting. So let's start by copying this and putting it here. Wow, okay, that's a little bit hard to read. Maybe I'll change how I'm looking at these so I can have them side by side. Okay, yeah, that's not too bad. So this should be 1 minus, so I'm going to do using, this is a little helper function that I made for doing integer powers of numbers. So this will be IPOW 2 of K. So that's K squared times X plus X. Well, I guess we could bring the X outside again, which is what the original function had. So yeah, let's factor out the X. Okay, so now we've got plus K times, for now, I'll just use the standard, like the standard library math functions, but we're probably going to want to change that later just because they're not all that optimized for what we're trying to do here. So that should get us our original function. But yeah, I think there's some ways that we can optimize some of this stuff later on, but let's just get it working first, and then we'll think about optimizing second, at least for the math part of this. So yeah, let's see, what can we do here? So we've got this first term. Which is going to be same thing, 1 minus K squared except we're going to want to have this over 2. And I'll put the x squared over here. So that's our first term from over here. Oh, actually, this shouldn't be const. So we're going to do that. And then I'm going to just have y equals a bunch of things. And then we'll return y. So maybe this will make things a little bit more readable. So the next term that we want here is going to be this sine term. So we know we're going to want the same sine term that we had up there. So I'll just copy paste that for now. That look okay? And then we're going to want to have that times x cubed and then divided by m squared plus 9. And then we're going to have another term out front, which will be, oh man, I was looking at the wrong function, m squared plus 4. And x squared, whoops. Actually, you know what? I bet we can pull an x squared out from all of this. Yeah, that should work. Let's do that. So I'm just going to move this to the very last step over here. And then everything else can kind of take an extra thing that doesn't need the y squared, or sorry, the x squared. So we're going to have that times our sine term. Actually, I'm going to move this up in front here. So we're going to have 2 times k divided by that term. And then this is actually going to be pretty similar, except it's going to be a cosine term instead of a sine term. So we're going to have mk times that business, and then this will be cosine instead of sine. So that looks about right to me, but obviously we'll find out in just a second. And then now we need the second antiderivative. So this is the dotted orange line from the Desmos graph. Actually, I'm gonna do something kind of similar to what I did here, but I'm gonna start inside and work outside. It might be better to rewrite that one as well, but yeah, it's okay. So let's start with our cosine term. So this is m over m squared plus 4. Right, and that's going to be times the same cosine term that we had up here. So yeah, you can see just from some of the copy and pasting that I'm doing that some of these calculations can probably be done once and then saved for later. But again, we'll deal with that. We'll deal with that in a minute. And then yeah, I'll do the same thing here where we pull out the x cubed. So this will be x cubed this time. Now here we'll do y plus equals kind of a similar thing to what we have here, except it's going to be a sine term instead of a cosine term. So here we'll have 6 minus m squared. Oops. Right, so now we've got the two sort of inner terms of these parentheses, and so now let's multiply it all by this k term. We've already factored out the x cubed, so I'm just going to do y times equals k over m squared plus 9 should be it. And then one last term here, y plus equals should be kind of the same thing we had up here, except with a 6 instead of a 2, right? Okay, so that seems right to me, but of course the only way to find out is to actually run it and see what we get. Actually, you know what? I made a mistake here. This cosine term should be a subtraction over there. Yeah, so these kinds of things are always a little tricky to implement just because there's a million places where you can make like a tiny typo, and it can be kind of hard to know. So I know some people have like code generation for this kind of thing, but I kind of like typing it out just because it helps me find places where I can optimize. But you know, maybe there's some middle ground there where you could get something that works as a sort of in between for that kind of thing. But yeah, it's okay. All right, so now we just need to actually implement this in the place where it's going to go. So yeah, I guess I'll set up the parameters that we had in the what do you call it? The parameters that we had in the Desmos example here. So the m and the k parameters, I'm going to set them up both as percent parameters for right now. So percent. I'm just going to call them k param and m param for now, even though those are pretty horrible names. And then we'll think of better ones later on. So this will be Waveshaper k. And we'll start at half, I guess. And then same thing for the m param. And then I'll show you in a second how we're going to map to the actual range that we need for the m param. So we'll add these to our parameter list. And here we're going to want the Smith Waveshaper. So I'll call this. This one doesn't need a lookup table, so I don't need to go through that stuff. Oh, and I guess we're going to want to add this Waveshaper to our enum up here. So yeah, what we're going to do is we're going to have a auto m range, and this is going to be a juice normalizable range. So this is going to go from 5 to 50, and we'll put the center at, I don't know, 15. We can change that later if we want. So for the Signal Smith Waveshaper, now we just need to prepare it with the sample rate, block size, and number of channels. Pair call. And now finally, we can just do this here. So else if params dot shape param is equal to the signal space shape. Then we can process our block. So we're going to need the K param. And for the M param, we're going to go M range, convert from 0 to 1. The same kind of thing. So that should get all of our parameters into that method. There's probably a cleaner way to do it, but for now, I think that'll be okay just to kind of test this out. So let's give that a try. Oh, I guess I haven't actually implemented the oversampling for this yet, so maybe that would be a good thing to do. I don't know if we'll get to that today, but maybe soon. Cool. Yeah. Any questions while we're waiting for this to build? Let's see where we're at. All right, we're almost there. Cool. So let's install the plugin and give it a try. Hopefully nothing breaks too catastrophically. All right, so we've got our full wave rectify that we had before. That's fine. And here's our new one. Okay. So we've got something interesting. That's kind of neat. Yeah. So we're getting these spikes here, which usually mean that the ADAA process is a little bit ill-conditioned. So I think I can adjust the tolerance to fix that. So yeah, but that's not bad. We're getting kind of what we expected as far as the shapes. And then, yeah, we can adjust our parameters, which is neat. And there we go. So that gets us back to our original sine wave. And then now we're getting some of this sort of fuzzy behavior on it as well, which is kind of cool. Actually, I bet this might help if I have the key follow of the oscilloscope follow the same frequency as the test tone that we're using. So this is 215 hertz. Yeah, that's fine. And then maybe let's normalize it, I guess. Yeah, so that's not bad. Let's just see if maybe we can tame some of these spikes that are shooting up at us. Actually, one other thing I should mention is that I actually haven't been listening to this. I have it on mute for now. And that's just like a safety thing. Like whenever I have a new wave shaper that I'm testing for the first time, I always just have it on mute just in case it blows up and, you know, don't want to hurt my ears or anything like that. And so when I actually listen to it, I'll put a limiter out front and then we can go from there. So let's set up our tolerance to be a little bit larger. which will trigger the fallbacks to happen sooner, which will hopefully stop the ill conditioning from being too crazy. So the other thing, the other thing was optimization, right? We're gonna do some optimization. So yeah, let's give this a try. Yeah, I might want to put some of these things in a CPP file as well, just to maybe speed up compile times and stuff, but we get there. Get there when we get there. Yeah, you know what? I'll do that. I'll start on that now, and next time we build, we'll have that. So since these are free functions, I think the static is redundant. Probably get rid of those. And yeah, then we'll move these other functions over as well. Oh, looks like our build is finished, so let's give this a try. Yeah, so I think I'm ready to actually give this a listen, but like I mentioned, I want to put a limiter on it just to make sure. Not Paul Stretch, peak limiter. Paul Stretch is fun too, but not when you're trying to protect your ears necessarily. All right, cool. So let's see what we get out of this. All right, yeah. That's pretty cool. So here, I'm going to turn the volume down just a little bit, and then I'll see if I can get this audio into Zoom, since I think that would be a cool thing to have. Let's see. So I want 3 and 4 going to black hole. Cool. So then let's see if we can do this. This will go to I want this to go to the black hole output. So I want to let me do that. What's going on here? Okay, output buses. Yeah, that should work, right? Interesting. Okay, well, I may not have my audio set up correctly for this to work right now, but maybe next time we'll get that going, or maybe I just need to activate the audio engine. It won't let me do it before. So that's it. Okay. Yep. So we've got that going to black hole, and we'll route this to black hole as well. So now the audio should come through black hole, and then I'm going to switch Zoom over to that as well. And at that point, most likely my microphone will drop out, and you'll just hear the black hole audio for a few seconds. Well, that's too bad. Okay, yeah, I guess Zoom won't let me route audio in. So yeah, I'll get that set up for next time though. And yeah, in the meantime, if folks are curious about this, I'll push my work when I'm done today, and then you can try it out yourself. But yeah, so that's some wave shaping right there. So we're still getting a little bit of wonky behavior. So I believe I may need to tweak the tolerance a little bit further. But let's finish refactoring this into a CPP file, and then I'll get that going as well. So yeah, so the tolerance, let's put this at what it was initially before we started today, which is that, and maybe I'll tweak that a little bit further later on. And then these member functions, I'll move to the CPP file as well. Cool, yeah, so that should be set up now. And I just have to add that to our CMake configuration. So Waveshaper, and this will be signal Waveshaper. And yeah, that should be working fine. Yeah, we may need to, tweak a few more things here and there just to get everything working perfect, but I think that should be fine to get us going here. Hopefully. There we go. All right, cool. So yeah, let's see, what time are we at here? Okay, it's about 4 o'clock. Yeah, I might call it a day here pretty soon, and maybe we'll get to the optimizations another day. So I'll put a note here to myself. But yeah, any last questions before we call it a day here? George wants to know if we can look at WDFs next time. Possibly. I've been trying to stick, not fully, but I've been trying to stick mostly to this specific plugin, and I'm not sure if there's something WDF related to do with this plugin at the moment, but I'll think about it. That is something I would like to talk about. So yeah, I'll think about how we can work that in. Do you have any suggestions, George? Actually, you know what? This is gonna bug me if I don't do just a tiny bit of optimization right now. Yeah. I'm gonna do a little bit of optimization, even though I said that I would wait, but I can't wait. I gotta do it. All right, so first off, on this one, I'm gonna make a little change to reflect the change that I made in the code, which is to pull out the x squared term, just so that everything's consistent if I go back to the Desmos page later. So we've got that. And then here we can pull out and a k over m squared plus 4. So this should be yeah, that should work fine. So I think that's all I can think of for the first antiderivative, aside from what I had mentioned about maybe saving the output of these cosine and sine functions, which I'll have to look a little bit more carefully about how that could be done. I'm also going to rearrange it similar to how we rearranged the 82 func. So let's see if we can do that. Auto y equals, let's do the cosine term first. So this will be minus m times our cosine term. Then we're going to do y plus equals, and this will be our sine term. So this will be 2 times this sine term here. And then we'll do y times equals this k over m squared plus 4 that we had looked at here. So I'm just going to copy that from here. And then we can make it a little bit neater. K over m squared plus 4. That's good. And now we need plus this term. So this is our term here. So y plus equals that. And we can get rid of a divide here by swapping that. Swapping that around. And then we just need to do our output like that. And that should work. Cool, so that's a little better. And now for this last one, I'm gonna leave, I think I'm gonna leave that other F2 even though we're not using it anymore, just so I don't get confused later if I come back to this, but we'll do x cubed times all of this, and that'll again help with reorganizing things. So we've got our k term there, and we've got that term there. Now for this one, I think we can pull out a 1 over m squared plus 4. So should be able to do that, and clean that up a little bit. Yeah, let's double check that that's still correct. Cool. Yeah, that looks about right to me. So that's actually very, very close to what we had in the previous one, just with some slightly different terms here and there. So this is just m times that. Then this is 6 minus m, so just the numerator part here. And then, oh, here, I was going to do this. Like that. I feel like I'm missing something. No, I think that's correct. K over that, 6 minus m squared for that. George says pre-compute the m terms to turn a divide into a mult. That's a little tricky because I don't always know what m is going to be because it might be smoothing or something like that. I was thinking specifically for this operation here, unless maybe you're talking about a different one. Yeah, there might be a way to do that. Keep thinking on that. Yeah. The ones that bug me the most, I mean, the divides are obviously not great, but the ones that bug me the most are these chain of things. Those are almost certainly going to be the most expensive. Actually, we could do like a sine cos function maybe to help out. We could do an approximation of log. Yeah, we got a lot of options as far as things we could do to optimize. But yeah, first let's see when these get called, just so we can see if there's ways to share things. So NLFunc82 gets called here with x0, right? Do we call anything else with just x0? I don't think we do. Yeah, because that's x0 plus x1. Yeah. Okay, so that one we probably can't do a whole lot with. There's these ones here with x bar. Yeah, that'll get a little bit tricky to get that worked out just right. I'm not sure. Yeah, I'm not sure there's a great solution for optimizing that. So maybe we can't pre-compute some of the cosine and sine things, but we should be able to compute them at the same time at least. So yeah, I've done this before. George is saying, I believe modern CPUs have sine cos ops, so they're not that expensive. I'm not 100% sure, but maybe let's find out. SSC intrinsics guide. Yeah, this if folks don't know about this page, it has some pretty good information on what instructions are available on your computer, or at least like more advanced math instructions. Yeah, okay, so it looks like we've got sine cos available on Intel for packed double precision. We could also SIMD this whole thing. That'd be interesting. Maybe we should do that. Oh, I don't know. That might take a little too long for today's stream. Maybe I'll do that later. Let's see if I think xsimd has a sine cos function. Yeah, they've got sine cos, so I could use theirs. Yeah. But the other thing I was noticing is that, so usually sine cosine implementations use an exponent function internally or something along those lines and so on. And we might be able to actually simplify that out, since we're doing basically we'd be doing the exponent of a log times a number. So maybe there's something we could do to help ourselves along there. So let me find my old implementation that I've done. I believe it was in here. Oh, that was sine h cosine h. Okay, yeah, for sine cosine, we may not need the exponent function. That might just be for sine for the hyperbolic versions. Exponential. Yeah. So I'm thinking there might be a way that could be even faster than sine cosine by exploiting this the fact that we're doing the sine and cosine of a log of something. Let's see. So cosine x is e to the ix plus e to the minus ix, and then the real part of that. So basically we would need the exponent of like the exponent e to the ix. So let's Desmos this again. You know what? So new graphing calculator, and so this will be y equals it's going to be the exponent of m times the log of x. And yeah, we'll have a slider for m again, right? So we've got something like that, right? So let's see. What's the log rule for that, right? That would be the same thing as y equals exp times log of x to the m, right? I think. Let's do the dash line thing again so we can see. Yeah, that looks the same. Interesting. Okay. And then, yeah, I guess we would want like, I don't know if Desmos will do this for me. Can I do the real part? No. Yeah, I don't know what Desmos lets you do with complex numbers. So I think there's something we can do along these lines to maybe get rid of the log and the or to do the log and the sine cosine kind of all in one trick like this. Yeah, this is a tricky one. I believe there's a way to do it. But I'll have to think about it a little more. So let's see. Real. Let me see if Desmos has a way to do what I need it to do here. Yeah, maybe not. All right, maybe this is something that I'll need like Python for or something. But anyway, yeah. So if this doesn't work out, then I can just do a sine cosine thing and go from there. But I think there's a way to do this. But anyway, I'm not sure I'll get to it today. Yeah, I'll keep this in the back of my mind for later. But yeah, anyway, thanks for hanging out, and yeah, I'll be back maybe next week or maybe another week with some more coding and some more plugin stuff. So yeah, see you all soon.